Steam enters a nozzle at 400 degrees C and 800 kilopascal with a velocity of 10 meters per second. So the properties of steam at the inlet are given. It leaves at 375 degrees C and 400 kilopascal. Properties at the outlet are also given, while losing heat at a rate of 25 kilowatt. Q dot out is given 25 kilowatt. For an inlet area of 800 centimeter squared, determine the velocity and volume flow rate of the steam at the nozzle exit. So we are interested in V out as well as V dot out. To solve the problem, I see that this is a steady flow process since there is no change with time. And for steady flow processes, we know that dt is equal to 0. So I need to work with conservation of mass and conservation of energy, or the first law, in rate forms to solve the problem. I'm going to start from conservation of mass. d and dt is equal to m dot in minus m dot out, since there is one inlet and one outlet. For steady flow processes, left-hand side is 0, so m dot in will become equal to m dot out, and I'm going to call it mass flow rate of steam. Conservation of energy, or the first law of thermodynamics, says dE dt is equal to E dot in minus E dot out. For a steady flow process, dE dt will become 0, so E dot in will be equal to E dot out, and we know the information for E dot. Q dot in plus W dot in plus M dot in times enthalpy plus kinetic energy plus potential energy per mass at the inlet will be equal to Q dot out plus W dot out plus M dot out times enthalpy plus kinetic energy plus potential energy per mass at the outlet. So let's simplify it. What do we know? There is no heat input. There is no work interactions, so W dots are 0. And I'm going to assume that there is no change in potential energy. So I see that V in is given, and I'm interested in V out, so I'm not going to get rid of kinetic energies. So what is left? M dot in times H plus kinetic energy per mass at the inlet is equal to Q dot out plus M dot out times enthalpy plus kinetic energy per mass at the outlet. So let's see what is given. V in is given 10 meters per second. Q dot out is given 25 kilowatt, and I'm interested in V out. What about enthalpies? We are dealing with steam, and I see that at the inlet, temperature and pressures are given. At the outlet, temperatures and pressures are also given. Based on the definition for a state postulate, two independent intensive properties are given, so I need to determine the state. Then based on the state, I can go to corresponding table and I can read for enthalpies, H out and H in. So let's determine the states. Input to the nozzle. Temperature is given 400 degrees C. Pressure is given 800 kilopascal. So I'm going to go to table A5, pressure table for saturated steam, because we know that saturated mixtures serve as the reference for us. At the given pressure, I'm going to read Tsat at 800 kilopascal. It is equal to 170.481 degrees C. I see that given temperature T in is greater than Tsat, so the state is superheated vapor. Now that I know the state, I can go to superheated water vapor table A6 at given temperature and pressure. I'm going to read for enthalpy at the inlet. It is going to be equal to 3267 0.7 kilojoule per kilogram. I'm gonna do the same thing for output. T out is given 375 degrees C. P out is given 400 kilopascal. So once more, I'm going to go to table A5 pressure table. At the given pressure, I'm going to read T sat. It is equal to 143.61 degrees C. I see that T out is greater than T sat at the given pressure. So once more, the state is superheated vapor. I need to go to table A6 and read for enthalpy at the outlet at T out and P out. It is going to be equal to 3221.8 kilojoule per kilogram. So now I have H in and I have H out. What about mass flow rates? So from conservation of mass, we see that m dot in is equal to m dot out, and we already call this m dot or mass flow rate of steam. So m dot of steam is equal to m dot at the input equal to m dot at the output. And what is the equation for mass flow rate? Density times velocity times area, or velocity times area divided by specific volume. So let's look at input and output. I see that at the inlet, velocity is given, cross-sectional area is given, and we know their state, so we can read for specific volume at the inlet as well. So I'm going to work with the properties at the inlet. Velocity at the inlet is 10 meters per second. Cross-sectional area is given 800 centimeters squared, and I have to convert it to meters squared divided by a specific volume at the inlet. So from table A6, I'm going to read the number for specific volume. It is going to be equal to 0.38429 meter cubed per kilogram. So I'm going to plug in this number here and solve for mass flow rate. It is going to be equal to 2.082 kilogram per second. So now that I know all the terms, I will put all the terms into the first law of thermodynamics and solve for the only unknown, which is V out. So let's plug in all the terms. M dot in, which is equal to m dot of steam times enthalpy in plus velocity in squared divided by 2. Do not forget the unity conversion ratio here, because we know that enthalpy is in kilojoule per kilogram. Velocity squared will be in meter squared per second squared. So I have to divide it by 1000 to convert it to kilojoule per kilogram is equal to 25 kilowatt plus mass flow rate of steam times H out plus velocity out squared divided by 2. One more time, I have to use the unity conversion ratio. I have to divide it by 1000 to convert it to kilojoule per kilogram. So now I'm going to have only one unknown, and I'm going to solve for V out. It is going to be equal to 260 meters per second. And we're also interested in V dot out. V dot out is equal to velocity times area at the outlet. So we just solved for velocity at the outlet, but area at the outlet is not known, so it's not going to be a helpful equation. What else? V is equal to mass times specific volume, or V dot is equal to M dot times specific volume. I'm going to write it down for the outlet. So V dot out will be equal to M dot out, which is equal to M dot steam, based on the conservation of mass, times specific volume at the outlet. And I can read it at T out and P out, somewhere here. So V out, I'm going to read for it. V out will be equal to 0.74334 meter cubed per kilogram. So I have this number, I'm going to plug it in here, knowing that steam was superheated vapor at the outlet using table A6, and solve for V dot out. It is going to be equal to 1.55 meter cubed divided by second.